Today's lesson is a continuation of section 8.5, write and graph exponential growth functions. Again, after we work with these now for maybe a day or two, working with exponential growth, and there's some things I'm hoping that you have started to pick up from exponential growth functions, things that happen when we're dealing with their graphs or the form of the equation in general, y equals a times b to the x power. Like I'm sure I've talked about too in classes, we can compare, I like to try to compare these two linear equations in terms of how we make them and things that happen with them, but we also are going to contrast them and show how they're different. Like sometimes we can take some of those same ideas from linear algebra, but apply them, or linear equations, but then apply them to exponential equations, like the idea that an exponential equation again increases much differently than a linear equation. A linear equation increases at the same rate as we increase x, but an exponential equation increases at different rates. It starts out growing very slowly and then increases very rapidly as we get to bigger and bigger values of x, which is one of my, here as I'm showing you, the top 3 things I want you to know about exponential growth functions. There are many important things to know about exponential growth functions, but I'm just going to list it down to a top 3, at least if nothing else, if you've kind of picked up on these 3, or at least kind of remember these 3 to start off, that's a good beginning for your knowledge about exponential growth equations. As x increases, the graph increases very slowly at first, but then very rapidly. So again, just show an example of that. First, I'll put a linear equation on there just to show you, this is what we've worked with for so long. Maybe something like this, just y equals x. This would be this equation right here, y equals x, which just goes up at about a 45-degree angle. But then if I do some kind of exponential, let's say y equals 2 to the x power, just something where we're even doubling every time. Well, again, I'll get to a point here where if I plug in 0, I'll get 1. I'll just pick out a few points here that I know very quickly. But something like this, an exponential growth function, remember, will start very close to the x-axis. In fact, it's very close. As the farther you go to the left on this graph, it'll get closer and closer. But it'll eventually start to grow here. And at the beginning, it's not growing very fast, but as soon as it hits its stride here, it would look maybe something like that, where now it's doubling every single time as I increase the value of x. And so this grows much more rapidly than a linear equation even. Somewhere around here, maybe they're growing around the same pace. But then the exponential passes that up and grows much faster as we increase the value of x. So one thing to remember about exponentials is they grow very slowly at the beginning. Again, in these stages, growing very slowly. And maybe they get to a point where they kind of start to pass a linear equation, kind of that kind of growth rate, and now all of a sudden increasing very rapidly as we get to bigger and bigger values of x. So that's one thing I'd want you to take away, kind of one of my top 3 things you should take away from exponential growth equations. Number 2, as again we talked about at the very beginning of that graph, what's going on there. At the very beginning, it increases very slowly. Exponential growth starts off very slow in low value in some of the lower values of x. And so we can even think of, well, if we decrease the value of x, like if we were going left on this graph and plugged in smaller and smaller values for x, we'll find out that the graph gets infinitely closer to the x-axis, but it'll never actually touch it. Going back to my graph here, this graph again, at this part of the graph, for my exponential, as I keep going this way, plugging in numbers that are more and more negative or lesser numbers for the value of x, I would find this line again will look very flat. I'll just kind of keep it going here. It'll look very, very flat, but really, it would be getting closer and closer to this x-axis. I'll extend that too. It'd be getting closer and closer and infinitely closer to that x-axis, but it'll never actually touch it. Why will it never actually touch the x-axis? Well, let's look at this equation here. I'm going to bring this back up. Y equals 2 to the x power. For this to be equal to 0, for this graph, at some point in my blue graph, for this at some point to eventually touch the x-axis, that means that I have to put in some value for x, and y would have to be 0. So at some point, this have to actually get down all the way down to 0 somehow. Well, can you think of a number that I can plug in for x here that would give me 0 for this problem? Now that's the trouble with this, because we can talk about plugging in lower and lower numbers, correct? Like negative values for x. Like if I plug in something like negative 4. Remember we talked about how to deal with negative exponents. Really, this is just like what? I'm just going to erase some things here to give myself some room. Really, this is just like what? Well, 2 to the negative 4th power is like 1 over 2 to the 4th power. What's 2 to the 4th power? Well, that's just 16. So this is now 1/16. Is that 0 still? No. Is it getting closer? Oh yeah, it's 1/16. It's a number pretty close to 0. Okay. What if I plug in negative 5? If I plug in 2 to the negative 5th power, well, that'd be like 1 over 2 to the 5th power, and that'd be like 1 over 32, 1/32. Is that 0? No, but it's closer than 1/16. So it's still not 0, but it is getting closer. What if I plug into the negative 6? And again, I think you'll start to see the pattern here, but if I plug into the negative 6, this is really like 1 over 2 to the 6th, which is just like 1 over 64. Is that even closer to 0? Yes, it is. So mathematics says, though, I can keep doing this. I can keep doubling that denominator. And I could have 1 over 64, or the next one to be 1 over 128, or 1 over 512 I'll get to at some point. Like if I just keep doubling. I can keep doubling that number, and I'll get a smaller and smaller fraction. 1 over 256, 1 over 512. If I keep plugging in more negative values for x, I'll keep getting a smaller and smaller fraction, but I will never get to 0. I always have 1 over something, even though it's 1 over some really big number. It'll still be 1 over something, so I can never get to 0, which is what I'm saying right here. And that's why this line will never, it'll get infinitely closer and closer to the x-axis as you go to the left here on this grid. But it'll never get to 0. And infinity and things like that, and limits, those are very tough concepts for any student to understand. And you'll see more and more of those as you get into high school classes. So if it's something that right now is still kind of tricky to understand, that's okay. But that's something you'll get better and better at as you see more of it. This is just your first example maybe of seeing something like that where a line can get infinitely closer to some number but never actually get to that number. And then going back to my list here, my third point, so talked enough about the second one there, giving you some example of how that works. But talking about the third one now, one more thing we should know is the growth factor of B. All right, growth factor, our B in our equation up here for an exponential growth equation, is what tells us how fast the graph will increase over time. Again, that's our growth factor. And again, I'd like to compare these to linear equations. Obviously, there's some major differences, but we can still kind of compare them to linear equations. And usually I'll tell students that's kind of like a slope. Like it's telling us how fast it's increasing. For a slope, it might tell us it's going up by so much every time. And it's usually adding that same amount. Again, for an exponential, it's like it's multiplying that same amount as we saw in the tables from the lesson before in our pattern. So if I had two exponential equations here too, something else I want us to realize, just kind of getting rid of, making some space here. If I have two exponential equations, let's say I have y equals 2 times x to the third power, and y equals 2 times x to the fourth power, I would want students to be able to realize which one of these is going to increase faster over time, which one will actually end up with bigger values of y as we plug in bigger and bigger values of x, or as we go to the right on this graph. Is this one, since it has a bigger, again, kind of like a bigger slope. It has a greater growth factor, so it's going to grow even faster than y equals 2 times x to the third power. This one, the first one here, the black one, y equals 2 times x to the third power, again, might look something like this. Again, you also can start really close, but they're increasing very rapidly, exponential growth. It did, just like most of these equations do. My green one here would have the same exact y-intercept, but it would actually just increase a little bit faster. And they might start off pretty close together, maybe even almost right on top of each other virtually. At least it will look like they are, but my green equation will actually increase faster because it's got a greater growth factor. So as time goes on, that one would definitely be above, you could say, above the green will be above the black one in the end, because this bigger number here says it's going to increase even faster than this one would. Then one more thing I'll talk about in this lesson as well is some problems or how to model certain problems with exponential growth. Problems we might see maybe on a test in my class or maybe on an MCA or just in some kind of real life problem. Certain problems that I might model with exponential growth and the way we typically do that. Again, exponential growth can mean that something's doubling or tripling over time. It can also just mean that it's going up by a certain percent over time. And again, that's maybe a typical way we might see problems too, where we've invested so much money in a bank account and our interest rate is, let's say, 4%, and it's going to increase every, quarterly or yearly or whatever it may be. Well, that's something that would model with exponential growth because it's going up by a certain percent of that number every time. And it's not saying like a linear equation. Like with a linear equation, let's say it's y equals 2x plus 50. So this would mean you got $50 in your account and you're just going to add $2 every time. Okay. Well, again, that's not what we're saying here in this case. For an exponential growth, we're saying it's going to go up by a percentage of that $50 every time. So it might look something like y equals 50. My initial amount times, and then a growth factor, and this little table here, or this little picture shows how to put together one of these equations. Let's say I'm getting an interest rate. I put that $50 in a savings account and I'm getting an interest rate that's, let's say, 3%. Then how would I show in an exponential growth equation that it's going to go by 3%, let's say, every year? Well, then it would look like this. 1.03 to the t power. T would be however many years later that I want to figure out how much money I'll have. Why is it 1.03? Because again, some people might say, well, I know 3% is just like writing 0.03, so you can maybe kind of see where that part comes from. But why is this 1 here? Well, if, again, something we'll realize more too when we go into the next section with exponential decay, is if I have a number that's in between 0 and 1, then I won't be having an exponential growth equation. It'll actually be something else, something that'll actually make the values go down as time goes on. So to have growth, I need this 1 in here, 1 plus whatever my interest rate's going to be. So if the growth rate was exactly 1, that means it'd be staying the same the whole time. So the 1, first of all, ensures that I'm going to have at least stay the same, and then whatever my growth rate is, that's like this 3% in this case. That's what makes it grow at that particular rate. So here's this exponential model, kind of like I've explained a little bit with that problem. But if you look at that, it's something I'd like you to copy in your notes if you're taking notes along with me. We've already kind of talked about how A is usually the initial amount in these problems, as it shows there. And we've talked about what the growth factor is. It's usually whatever is to a power, this b, that's my growth factor. Well, in this case, for this problem, because they have the 1 plus whatever my rate is, it's that whole thing. That's the whole thing is my growth factor. Whatever rate we're talking about, my growth rate, just like I showed in the example problem, it's just this r right here. Whatever that number, that percentage is I'm adding to 1 to make it increase, to make it grow. And t is the time period we're talking about. So again, after however many years or however much time, that's how I'll know. And that's what I'll plug in to find out, well, after how much time do we have this much population, or how much time do we have this much money in the account, or how many cell phones are actually in circulation. Like, and that's the amount of time we'll plug in to figure out our answer. So here's an example of a problem that talks about population growth, a problem where we might use an exponential growth equation, something like this. It says the population of Plainview is about 3,100 people right now. They say that the population is growing exponentially with a growth rate of about 1% each year. So if this is true, what would be the population in 2020, or in 2120, or in 3020, any of those years? So we could set this up with some kind of exponential growth equation. Well, we've talked about how the initial amount is usually my A, so I think we can figure out, I'll ask students, but usually we can figure out right away that 3,100 is going to be my A, my initial amount that I'm starting with here. That's my initial population. And my B, my growth rate, well, in this case it's 1%. So to make this grow at 1% every year, however many years I'm talking about, I'm going to have it as 1.01, and then to the t power again times how many years after how many years am I trying to figure this out for? If I'm talking about 2020, well, I guess that'd be right now that we're going to talk about this being 2013, I guess, right now. So what would I put in? I put in, I guess, 7 for the year, because it'd be 7 years later. And I would figure out my answer here. And doing the math in my head, I'm getting about 3,324 people, something like that. So, yeah, just guess it. Just kind of mental math, thinking it out. Just kidding, I have a calculator right here. So, but 3,324 people. So, after 7 years, we're estimating that's what the population would be if it grew at this 1% rate for that amount of time. If I was going to set it up for the next one here, so let's say what about for 2000 or for 2110 that year? So 107 years later. Well, again, the equation would start out the same, 3,100 people. And my growth rate is still the same we're talking about, 0.101 or 1.01. But now I'm talking about, well, 107 years later, so 107. So I'm going to plug into my calculator, and I'll do that. I'm getting 8990 about for the population here, so about 8,990 people. Now, if it kept growing at that rate, about 100 years, the population would over double there. So that's what I'd be finding out. And if I want to do it for the very last one there, well, what about in 1,007 years? Which again, maybe a little unrealistic. So, but let's see what it gives us if this kept going at this rate. 1% for 1,007 years. Well, we end up getting, if we punch that in, again, we take 1.01 to the 1,007th power first, and then times that by 3,100. Well, for this one, I'm getting 69,660,260 people. So, again, exponential growth, there's a good example right there. I mean, it took a long time, but exponential growth, once it got going, once we put in a bigger and bigger values for x, well, it grows much quicker here now that we're up into the numbers in the millions. So exponential growth, and one thing I'd like you to take away, something like that. Here's how we can set up some kind of problem. But just recalling that, yeah, as the numbers get bigger and bigger, it starts growing faster and faster.